In this video, I'm going to talk about resonant frequency. What is resonant frequency? This resonant frequency happens in RLC circuit. It could be RLC parallel circuit or a series circuit. Here, I'm going to talk in RLC series circuit, R, L, and C. Okay, assuming that's a AC source. Okay. So in RLC circuit, at one frequency, the inductive reactance and capacitive reactance are going to be equal. They cancel out each other because one is positive, another one is negative. So the circuit is going to behave like a resistive circuit. So that is called the frequency at which an RLC circuit is going to behave like a resistive circuit is called resonant frequency. Okay, so here you can see RLC series circuit. So JXL is inductive reactance is J omega L. XC equal to capacitive reactance, which is minus JXC. Inductive reactance we always indicate positive, capacitive reactance always indicate negative, and Z is the impedance. So Z equal to R plus JXL minus JXC. So if you look at this equation at one point, as frequency changes, as frequency increases, JXL is going to increase, JXC is going to decrease. So at one point, they're going to meet at one point. That frequency is called resonant frequency. So if you look at this circuit, if you look at the RLC circuit, what I'm saying, at resonant frequency, impedance equal to R. So basically JXL equal to JXC minus JXC. So basically XL equal to XC. So XL is nothing but omega L. XC is nothing but 1 over omega C. So omega square equal to 1 over LC. So here that resonant frequency, we call this as omega naught. So I'm going to represent this as omega naught. So omega naught equal to 1 over square root of LC. Okay, and when it comes to the frequency, this is angular, resonant angular frequency. When it comes to F naught, 1 over 2 pi square root of LC, and this is valid only for RLC series circuit. You cannot use these formulas for any other circuit. So next examples, I'm going to solve different examples or RLC series parallel combination of circuits. In that case, you have to find F naught for each example by making the imaginary quantity equal to 0. Now I'm going to draw a graph for the voltage and currents. So here is my time. So what happens so basically, let me take this as a frequency or omega instead of time, sorry. So let me take a y-axis as the current. So what happens at one frequency, as omega changes, XL is increasing, XC is decreasing, right? At one point, you will see the maximum current. That maximum current we see at omega naught. Okay, this is resonant frequency. This is the graph for a current. At the same time, if you draw a graph for impedance in RLC circuit, series circuit, impedance, what happened? At resonant frequency, you will see the lowest impedance. So this is impedance and this is current. My apology, that's current. Okay, so at resonant frequency, you will see maximum current passing through the circuit. At the same time, since the current is maximum, power is going to be maximum. At resonant frequency, power consumed with the circuit is maximum. So if you look at this RLC series circuit, at resonant frequency, power consumed with the circuit is at resonant frequency, power is maximum, current is also maximum, and minimum impedance. Now I'm going to define two more terms called half power frequencies. So half power frequencies are frequencies at which the power consumed by the circuit is half of the maximum value. So here the current is going to be basically square root 2 times I, 0.707. So these half power frequencies, omega 1, omega 2. So omega 1 and omega 2 are called half power frequencies. Half power frequency. Okay. At half power frequency, power consumed with the circuit is only half of it. So half of the maximum value. At these frequencies, so at omega 1 and omega 2, power consumed by the circuit is half of maximum value. So now another term we define is called bandwidth. B we indicate with bandwidth. Bandwidth equal to omega 2 minus omega 1. Okay, I'll talk about bandwidth in a sec. So basically bandwidth is nothing but it's a frequency between two half power frequencies, or the difference between the higher half power frequency minus lower half power frequency.